Welcome back to Summarize Science, where we break down complex research into plain English. Have you ever tried to zoom in on a photo only for it to become a blurry, pixelated mess? This is a classic problem in photography known as low-resolution imaging. Usually, scientists use artificial intelligence or image priors to guess what those missing details look like. However, these AI methods can sometimes hallucinate details that were never there in the first place. They rely on huge datasets to make an educated guess about the underlying picture. The researchers behind this paper have developed a new approach called multi-scale super-resolution that avoids the guesswork. Instead of using AI, they show that we can use data collected at different scales to resolve the image. Scale refers to the effective pixel size, which changes depending on the sensor or the zoom of the lens. The secret lies in taking multiple low-resolution pictures at slightly different sizes. Think of it like trying to measure a gap with several different rulers that have different markings. By using pixel sizes that are coprime, meaning they do not share any common factors, the images provide unique pieces of a puzzle. For example, if one sensor uses 17 unit pixels and another uses 18, they capture different information about the same scene. In a two-dimensional image, having at least 3 different box sizes is enough to reconstruct a sharp final picture. This is because the different scales fill in the blind spots that a single camera would naturally have. The researchers used a mathematical tool called a Fourier domain technique to combine these measurements efficiently. They proved that as long as the pixel sizes are chosen correctly, the math always finds a stable answer. To test this theory, they used a specialized CCD camera and a technique called hardware binning. This allowed them to artificially group pixels together to simulate cameras with different resolutions. They tested this on one-dimensional targets like bars and two-dimensional targets like photos of trees. When the pixel sizes shared a common factor, like 12 and 15, periodic errors and artifacts appeared in the results. But when the researchers used coprime sizes, like 13 and 16, the errors vanished. This confirmed that the choice of scale is the most important part of the process. In the 2D experiments, they were able to reconstruct images that looked just as good as those taken with high-end sensors. Even though the initial data came from sensors with pixels nearly 20 times larger than the target resolution, the detail was recovered. You can see the difference in these Air Force resolution targets and images of a pinwheel. As you add more scales, the error in the reconstruction drops significantly. Moving from 2 scales to 3 scales drastically reduces the noise and prevents weird artifacts from showing up. The beauty of this method is that it is incredibly fast and could be built into modern smartphones. Many phones already have 3 cameras with different lenses, which could provide the exact data needed for this math. It could also be used in drones and microscopes to get clearer views without needing expensive hardware upgrades. To recap, this research shows that well-posed math can solve the super-resolution problem without relying on AI hallucination. By combining images from different scales, we can perfectly reconstruct high-detail scenes. In the future, your phone's digital zoom might finally be as sharp as a professional optical lens. Thanks for watching Summarize Science.